All righty. So when last we met, we'd been talking about the different types of radioactive decay. And one of the things that's important to know about radiation is how do you protect yourself from it? So shielding is the way that we protect ourselves. Now, alpha particles are big and charged, and they can be incredibly damaging. And we're going to talk a little bit more about that when we get to effective dose at the end of these notes. But the nice thing about alpha particles is they are the very easiest to block. You can literally block them with a sheet of paper because they are big and they are charged. And so that makes it very easy to block the view of them, or to block them from damaging tissue. And then beta particles are the next largest. They still, because they're so much smaller, they do require a more thick material to block, like concrete or something like that. But still, they are a physical particle and they are charged. So they want to interact with something, and they'll interact with the shielding material. Your gamma rays are more difficult to stop because they, things like gamma rays and X-rays, because they're photons. They don't tend to interact with matter very easily, and they don't have mass. So they tend to be the harder ones to block. And so, like, if you think about like an X-ray technician, they're going to wear that lead protective gear, or they're going to get behind a wall or something like that. It usually has a lead barrier of some kind in it. So just here's a little cartoon that kind of shows that. So, it depends on the material. Now, direct exposure to any of these is not good for living tissue unless it's done in a controlled way. Obviously, we use these things in cancer treatment. We use gamma rays or X-rays, or sometimes electrons are used. Alpha particles are generally not used, but when I was a senior in college, I worked at the cancer treatment clinic, and I was a treatment planner. So I would sit down and do the calculations of how much exposure you got on the machine based on your particular tumor and where it was located and what kind of treatment plan they had described. So I was the one sitting down calculating how long basically they left you in the machine. Well, we had a couple of different machines. One of the machines we had was a traditional X-ray therapy machine that was like an X-ray that you would take pictures of broken bones or whatever with, but the beam was much more intense. And what they would design it to do would be to penetrate and deposit most of its energy, what's called the Bragg peak, at the site of the tumor. And there's different depths that those different types of radiation will penetrate into the tissue. And you knew this, and so you figured out, how long and based on the X-rays where and all that. But we also had an electron machine. And the electron machine, because the X-rays would penetrate in too deeply to be effective on like things very close to the surface, we would use electron therapy for things like salivary glands, or things in the jaw or the mouth, or sometimes the throat area, or close to the surface of the skin, because they didn't penetrate as deeply into. So sometimes you want those things to penetrate into the tissue so you can kill the bad cells. So when you calculate how radioactive something is, the activity is literally the count of the decays per second of that particular isotope. And it depends on, that particular isotope's nuclear physics. There's no way to predict it. It just has to be measured. And so the rate then, or the amount of radiation you receive, is the activity, is the number of parent nuclei you start with, obviously how much do you have, and then lambda, which this should be a lowercase lambda. It's decided it was going to uppercase it for me, but that's the decay constant. That's the inverse. It's inversely related to the half-life. So the decay constant is unique to the nucleus. It has to be determined experimentally. You don't know what it is, but you look it up. So it's something you look up for the particular isotope that you're using. So if we want to know how many are left after a certain time has passed, it's related to this activity rate. So the number left, which is here, this is how many's left, is equal to what you started with multiplied by the exponential decay constant. Okay, so the exponential, when we talk about radioactive decay, it's an exponential activity. So what happens is after each half-life passes, 50% of the sample you have remaining is going to decay. So let's say I start with 10 kilograms. So after one half-life, whatever it is, whether it's 5 days or 100 years or 1,000,000 years or whatever, you start with 10 kilograms. After one half-life, you'll have about 5 left. After the next half-life, you'll have about 2.5 left. After the next half-life, you'll have 1.25 left. So it's an exponential decrease in the amount of material that you have that's governed by that decay constant, which is determined by the half-life. So you need to know what you start with, because obviously the amount of material you start with is going to determine what you have left. Okay, so the mother product is the one that's doing the decaying. It turns into the daughter. So it kind of shows you this little step of what's left after each half-life. So the rule of thumb is usually after about 5 half-lives, enough of it is decayed away that it's not considered to be detectable anymore. But again, remember, it can turn into something else that's also radioactive that then has to decay also. So that's what takes the time. Most of the time, it's not going to immediately decay into something stable. It's going to have to go through a couple or 3 steps at least, and sometimes many more than that, to get to a stable nucleus. But it will keep producing radiation until it reaches a stable nucleus. So whatever it turns into, if that's not stable, it's going to have its own decay mode. It may be the same as the mother. It may be different. It just depends on the stability factors of the nucleus. And until that thing reaches a stable configuration, it's going to continue to be a radioactive isotope, whatever it turns into. So there's different ways. The MKS unit to measure radioactivity is the becquerel, which is one decay per second. 1 decay per second. But in medicine, sometimes you see the unit of the curie. And the curie is based on radium. And a curie is like 10 to the 10th becquerel. So because radium is highly radioactive, Marie Curie discovered it. And so the unit is based off of radium, and it's named sort of in her honor. But you will see that as a very often in nuclear medicine applications, instead of given in becquerels, it'll be given in curies. Okay. Kimmy, this is not a good time. Okay, so how to determine if something is stable or not, there's a few different rules. Now, first of all, we've already mentioned one. The larger the nuclei, the more unstable it gets, because you start getting too big for the strong nuclear force to be effective anymore. And so larger nuclei tend to be unstable. So anything bigger than 83 is an unstable nucleus. Okay. Now, and I mentioned about 2,500 to 3,000, depending on what source you look at and how they define what an isotope is, because some of these ones are like, they're just made to see if they can make them in a lab, but only about 300 of them are stable. So when you look at the smaller nuclei, you want approximately the same number of protons as you do neutrons to screen the protons. So if you have an atomic mass number of less than 40, which is around calcium on the periodic table, because calcium is 20, you need about the same number of protons as neutrons. If that number is out of whack, either too many neutrons or too few neutrons, that thing will be unstable. But the problem is you start getting into larger nuclei and more protons, you start needing more neutrons per number of protons. And it's about 1.4 neutron for every proton you have to be an effective screening for the protons to prevent the Coulomb force from repelling them. So like your big nuclei tend to have like uranium-238. Uranium is 92, so it has 140 something neutrons to be able to be stable. Tammy, you hadn't wanted me to pay attention to you in like 3 days, and here you are. Okay. The other thing is there's rules about pairing. So there is rules about odd, even, whatever. So when we talk about this pairing rules, it's the number of protons and neutrons. So if, for example, both those numbers are even, so you've got an even number of protons and even number of neutrons, the nucleus tends to be more stable. If both those numbers are odd, the nucleus is very unstable. And in fact, odd nuclei are inherently radioactive except for the smallest ones. So lithium-6, for example, is 3 protons and 3 neutrons. That's a stable nucleus, but only because it's so small. The largest odd nucleus that's stable is vanadium-22, and vanadium is atomic number 11. So that tells you there's not a lot. So that's why when we talked about like technetium and protactinium, they are inherently unstable because of that odd relationship. But the next one is odd even, or even odd, like odd numbers of one and even numbers of the other, and protons and neutrons tend to be stable if they follow the other rules. If they follow the other rules about number of neutrons, size of the nucleus, and so on. Okay. Now, the other thing that happens is binding energy. Binding energy also determines the stability of the nucleus. So remember, there's that one graph that shows that the radius of the atoms get smaller as you get these closed electron shells. Well, binding energy kind of works the same way. There's different models of the nucleus, and they both are kind of right and they're both kind of wrong. And one of them is the shell model. The shell model says, okay, we have kind of like nuclear shells, just like you have electron shells. And when you get a full nuclear shell, that tends to be a more tightly bound nucleus that wants to kind of hang on to its nucleons. So what happens is there's sort of a peak of binding energy. And I think I've got a picture on the next one here. Oh, not yet, but that peak is what determines that. So this binding energy shows up in this weird way that if you take, say, a nucleus like, I don't know, carbon-14, we've got 6 protons and 8 neutrons. If you take the mass of a proton and multiply it by 6, and you take the mass of a neutron and multiply it by 8, and you add that number up, then you take the mass of a carbon-14 nucleus. That carbon-14 nucleus will be less massive than the pieces that went into it. And I know that sounds weird, but what that is that's something called the rest mass, or the rest energy. The rest energy is the energy required to bind that nucleus together. So it actually robs the mass in a way and makes the mass smaller, but that's what we get back out when we break that apart, okay? So the pieces actually have a larger total mass than the final nucleus does because of this binding energy. So the higher the binding energy, the more stable the nucleus, the harder it is to break it apart. Now, when you look at the binding energy curve, that determines whether the atoms, or the nuclei tend to undergo fission or fusion, because they're trying to get to that most tightly bound state. And depending on which side of that number they're on, they're either trying to get bigger or they're trying to get smaller to get to the top of that hill. Okay, so fusion to get bigger or fission to get smaller. So here's the binding energy curve. Now, right here is the peak. The peak is, we call it the iron peak in astro, but the iron peak is where the tightest bound nuclei are at. And in fact, the tightest bound nucleus is iron 56. Okay, so what that means is all the elements down here are trying to undergo fusion to get to that peak, or easier to fuse. All the elements over here are bigger and want to get smaller, so they're easier to break apart, so undergo fission. Now you'll notice there's some zigzaggy lines here, and that's the odd even business, okay? So like lithium-6 is way down here because it's an odd nucleus. Helium-4, though, is up at the top of the hill because it's an even nucleus, and plus there's something else special about it. There's also peaks at carbon-12 and oxygen-16. So everything, ideally, the nuclei themselves, the tighter bound they are, the more stable they become. So iron, what that means is iron cannot naturally undergo fusion. Okay, and that may not mean anything to anybody except an astronomer, but that's why we have supernova, is because really big stars, when they fuse and fuse and fuse and they get to iron, then they're done. They can't do anything else, and gravity causes them to detonate. So this other thing that's going on with these nuclei is something called magic numbers. And it's a lot like having the closed electron shells and having the inert gases, which they've got that full electron shell, so they don't want to interact with anything. You also can close these nuclear shells as well and make these nuclei not want to interact with anything. So we call these very fancifully magic numbers, okay? And so there are nuclear shells. When you fill them with a magic number of nucleons, they become very unreactive and they close and they don't want to interact. So what that means is that's a very stable nucleus, so there's going to be a lot of that nucleus hanging around. And that's why we have the peaks, where we had the peak at helium-4 and the peak at oxygen and the peak at carbon. Those happen to be magic numbers. So the magic numbers don't seem like they follow a pattern, but 2 is a magic number. So helium-4 has 2 protons and 2 neutrons. So we call it a doubly magic nucleus, which I always think is funny. It's doubly magic, so it is super stable. Oxygen 16 is doubly magic, okay? Remember I said the element tin, TiN, had 10 stable isotopes? That's because 50, which is its atomic number, is a magic number. Okay. The interesting thing to notice is 126 is a magic number. And one of the things that people think might happen is, you know, we've got all these new elements, and we're going to have a group probably talk about those in the presentations, but those things have really super short half-lives, like millionths of a second. There's some thought that maybe if we got out to element 126, it would be a stable element, or we would reach what was called the island of stability. Now, it may mean stable in that its half-life is seconds instead of millionths of a second, but that it's much longer lived than everything around it, because that's a point of a magic number closing that shell. So if you have either one of these numbers show up as your proton or neutron number, it's a magic nucleus. And then if you get protons and neutrons are both magic numbers, then that's a doubly magic nucleus, and that's extra stable. So, you know, sometimes we get fancy in what we call things. Okay, so these elements have a lot of stable isotopes. So here, for example, is your iron nucleus is at a peak because it has a type, it has the peak of the binding energy, but it's not a magic nucleus. Now, then you get these zigzags in this curve because of the zigzag in this curve because of the odd-even or even-even or odd-odd relationship. But the peak, like at n equals 50 or z equals 50 or n equals 82 or whatever, those are abundances due to the magic numbers. Okay, so that has nothing to do with odd-even or even-even. Those are the magic numbers. And then you'll see that out there at lead 108, lead 108 is very abundant because that's a doubly magic nucleus. So see how it's very much more abundant than the stuff coming up to it. And then beyond that, we have bismuth, which is stable, but after that, everything else is radioactive. So when we look at these, how these elements exist in the universe, this is what decides that. Where is it based on the binding energy? Is it odd, even odd, whatever? And then is it magic or not? All these things, which is kind of fun. So this is just a little chart that kind of goes over all those rules. You can look that up in your notes. Now, the last topic that I want to talk about in these notes is something called the dose. And this is where you get into stuff like you talk about in radiation therapy or nuclear medicine or whatever. So we are exposed to radioactivity every day, okay? We are exposed to radioactivity every day. It's naturally occurring. You know, I just ate a banana. Bananas have potassium-40 in them. Okay, potassium-40 is a radioactive isotope, but our species has evolved to deal with this exposure. You know, the sun gives off radiation that sometimes makes it through the atmosphere. Carbon-14 is in our bodies. You know, we live in buildings made out of brick or stone or mortar or whatever. Okay, so this is the background level of radiation that we're exposed to. The dosage is sort of the amount of that we're exposed to sort of annually or yearly or whatever. Okay, so the mechanism to measure dose, first of all, when you talk about radioactivity, there's sort of levels of where you're at. So the first one is just how much energy is given off. And that doesn't take into account, you know, what kind of particle it is, did it do any damage to tissue, whatever. There's just this much energy. But then we talk about that energy being absorbed by matter. So by living tissue, by a kilogram of living tissue. So that's what the absorbed dose is. It takes that energy per kilogram. So joule per kilogram of absorbed dose. But we call that in MKS units a gray. Now, grays are seen sometimes in medical applications, but you also see rads, which is radiation absorbed dose, and a rad is 1/100th of a gray. So when I was doing treatment planning, we did everything in rads. And that just, what that does is that doesn't take into account the type of radiation. It just says the amount of energy per kilogram that gets absorbed. Now, here's the thing though, not all radiation is the same. Remember I said that alpha particles are big and they're charged and all that. So there's another step we can take that actually takes into account the type of radiation that you have. And that's called the effective dose. The effective dose takes the absorbed dose and multiplies it by a scaling factor depending on what type of particle it is. So we measure that in either rems or sieverts. If you're starting with grays, it's in sieverts, and you're starting with rads, it's in rems. So rems is the radiation equivalent damage to human, basically. Okay, so what it does is you have to look up this scaling factor. Some books call it the RBE, which stands for relative biological effectiveness, and some call it the QF, or the quality factor. Different books call it different things, but what it is the scaling factor that takes into account how big is the particle, is it charged or not, and how fast is it generally moving. And it'll give you a number. So for example, an alpha particle has a quality factor of between 10 and 20, depending on how fast it's moving. The faster it's moving, the higher the number. Whereas a gamma ray has a quality factor of 1. So the equal amount of rads is 20 times more damaging if it's done by alpha particles than if it's done by gamma rays. Does that make sense, I hope? So it weighs these particles more heavily. And so you just take your rads and multiply by your scaling factor for that particular particle. You just look it up. So this little chart, you can just look at it for your own because it's kind of hard to see on here because the screen is so small. But what it does is it looks at your exposure, you know, where your relative exposure is. And so like it starts with the least amount is over here in the blue, the upper left-hand corner is the least amount. And then that whole blue box fits into the top left hand of the green box, and that whole box fits into right here, and then that whole box fits into right there. So it kind of shows you what the exposure is. And this box down here is the Chernobyl radiation accident. So, you know, we do get exposed to different amounts of exposure in our lives, depending on, have we had x-rays? Where do we live? You know, and these are just some different examples. X-rays have different amounts of dosage. So like a CAT scan is a very large amount of radiation. So that's a full body CT scan. You can see here it's got 100 times the dose or the exposure of a chest X-ray. And that's because it's basically a full body scan. It's usually more intense because they're trying to see stuff. So CAT scans are sometimes counterindicated for certain classes of people that might be susceptible to DNA damage. You know, and a healthy adult human, they usually don't consider it a big deal, but like in a developing child, they try to avoid CAT scans for them. Pregnant women, they try to avoid CAT scans. But also where we live. So the higher in the atmosphere we live, in other words, the greater the elevation we're at, the less protection we have from the atmosphere. So we get exposed to more like cosmic radiation. And then this shows the different things that happen when you're exposed to radiation. You get radiation sickness or radiation poisoning or whatever. But we are exposed to radiation just in our day-to-day lives. Most natural background radiation is most of our exposure. There is still fallout from the atomic weapons testing done in the 40s and the 50s and the 60s. It's still out there. There are consumer products that have radioactive materials in them. Your smoke detector has a radioactive chip in it. That's how it works. It has a little chip of americium in it that's giving off alpha particles, and there's a little detector in there. And as long as there's, and remember, alphas are easy to block. So smoke gets in there or steam gets in there or something happens and it changes the amount of detections that thing gets, it goes off. Like I said, bananas, Brazil nuts, any leafy greens. Carbon-14 is in everything because it's either in the plants you eat or it's in the thing that ate the plants then you eat. So, we have natural exposure. And then just the ground, like I mentioned, there was radium in the ground or radioactive isotopes in the ground, and more or less, depending on where you live. Depends on how much of the igneous bedrock is exposed where you live. Here in Arkansas, we were kind of in the lower end of that because we have a lot of ancient seafloor over the igneous rocks because we were under the Gulf of Mexico, billions or millions of years ago, whenever it was. So that's just another little graphic that kind of shows you that. But there are places where you might not expect it. Okay, there's places where you might not expect it. Like, for example, if you go camping and you use a Coleman fuel lantern, camping fuel, or what we call white gas fuel lantern, the mantles of those lanterns are coated in thorium because that keeps them from burning up. Or if you have a glow-in-the-dark wristwatch, that's sometimes painted with tritium paint. So there's places where you might not think about it being, but it just kind of shows where these places might show up. So, okay. All right, let me turn this off.